Section 8.1 is going to discuss kind of the basics of hypothesis testing. This is where we start moving away from something that could kind of be considered math and into statistics. We're going to stop describing things and going beyond our data to make hypotheses and test those hypotheses. So this is going to be distinctly different than a math class, where in a math class you prove things. Here we don't. Now, we are going to start out by testing claims about a population parameter. And those claims are tested in what's called the null hypothesis, H sub O. Now let me mention something about the null hypothesis and then ask you a question that kind of follows up on it. And that is this: HO will contain a statement about a population parameter. Now, what are examples of our population parameters? There's 3 of them that you can give me. So here's your part in this. What would be an example of a population parameter? No examples? Just give me the symbol. No? P hat is a sample statistic.
P.
S is also a sample statistic. P, all right, P, sigma, one more, and mu. So at least initially, our null hypothesis is going to test claims about one of these 3 parameters. And those claims are going to contain the condition of equality. So let's see, these statements, including the possibility of equality, must be part of HO, that is our null hypothesis. So when you're stating these claims, not only does the symbol have to be part of your null hypothesis, but one of these 3 things: equal to, less than or equal to, or greater than or equal to. My stat disk is going to use just equal to. I do it this way just to make it a little bit more user-friendly. But both of these are going to be part of your null hypothesis. One of these and one of these. Now your alternative hypothesis is going to contain what's true when your null hypothesis is not. So for instance, let's take a look at example A down here. It says that a majority of adults would erase all of their personal information on the internet if they could. So if we want to turn that into a hypothesis, the first thing we got to do is understand what parameter we're working with. Are we working with P, sigma, or mu down here when we're talking about the majority of adults? Well, let's maybe back up a second. What does mu represent anyways? What kind of mean? Is it a sample mean?
Population.
It's a population mean. So what I'm trying to get at here is that there's a difference between a parameter and a statistic. What is that difference? What makes something a parameter? What makes it a statistic? They're both characteristics of data.
A parameter is a characteristic of a population, whereas a sample is whereas a statistic is a population of a sample.
Statistic is a characteristic of a sample, yes. So a statistic is a characteristic of a sample. A parameter is a numerical characteristic of a population. So of these 3, proportion, standard deviation, or mean, which one sounds relevant to the majority of adults would erase all their personal information on the internet if they could?
P.
P. Now, This part is, this is the harder part with this one because it's not explicitly here. And that is, at what percentage constitutes a majority? At what point do you win the election? What percentage of the vote do you have to have?
Over 50, 51.
Over 50. So it'd be P is greater than 0.5. That's what they're going to be asking you to put in this first little slot here. It says, express the original claim in symbolic form. Let the parameter represent the adults who would erase their personal information. So you have to put in three things. You have to adjust this to the drop-down menu to get the right parameter, and then the greater than, and then 0.5. There's a problem with this though. That doesn't contain the possibility of equality. So that's going to go in your alternative hypothesis. So that's going to be, depending on if you're me or the book. For myself, I like to write it HA. The book and my stat disk are going to write it with H1. That's okay. Either one's fine. But we'll just stick with HA. It's just a little bit nicer. A is for alternative, a little bit of mnemonic. So this has to go as part of your alternative hypothesis. P is greater than 0.5. All right, that's cool. Now your null and alternative hypothesis are set up like sides of a coin. You're either heads or tails. There's nothing else. You're one or the other. So what would be kind of the opposite of this? What's the opposite of P is greater than 0.5? P is less than 0.5. Now when I say your heads or tails and nothing else, this actually leaves room for a little something else. Yeah. Thank you, squared. Cubed. Is it coming? Yeah. It might come later. You have to have less than or equal to. That way you're one or the other. All right, you have to fall in one or the other. You can't leave room for kind of a third option. So it's called mutually exclusive, you're one or the other, and exhaustive. And that's it. Those are the only possibilities. Not something you need to know, but I'll throw it out there in case you see it. So when you answer this on my stat disk, you're just going to have to use drop-down menus to find the correct notation. And like I hint, well, maybe I haven't really hinted at it yet too much. My stat disk is not actually going to use the less than or equal to. They're going to use just equal to. So your answer there is probably going to be stuck with P is equal to 0.5. That's okay. I like writing it this way because it's easier for you. And that's it. There's your null and alternative hypothesis for this particular claim. Here's your claim. That becomes part of the alternative hypothesis. And then this is in your null hypothesis. We're okay with that first example? Yes.
HA supposed to be P is greater than equal to or no?
No. In the alternative hypothesis, you will never have the possibility of equality.
Okay.
It always has to be a greater than. So if you wanted a majority, if you had exactly 50%, then you wouldn't win the election. It'd be a tie. You'd have to go to a runoff or something like that. So if you want a majority, you have to have more than 50%. And that, the fact that it doesn't have the equal to part puts it in the alternative hypothesis. So yeah, you'll never have an equal to as part of the alternative hypothesis. Okay? Appreciate the question. Anything else on that one? Okay, so let's take a look at the next one. The mean pulse rate. So let's just stop right here. What parameter do you associate here? Mu. All right, so mu in beats per minute of healthy adult males is 68.8. Okay, so that's our original claim, at least in words right here, the stuff that I've highlighted. Let's express the original claim in symbolic form. That'd be mu. What does the word is translate to?
Equals.
Equals 68.8. Nice. Fatal. Should that be part of the null or alternative hypothesis? Yeah, it has to be part of the null because it has the possibility of equality. Now keep in mind the heads and tails kind of nature with null and alternative hypothesis. If you're not heads, then you're tails. So if you're not equal to 68.8, if this is false, then what has to be true? What should I put here?
U is greater than.
Not equal to. So you're either equal to 68.8 or you're not equal to 68.8. Those are your two choices. And to kind of round this out a little bit, let me give you one last example. Let's do the claim. There's the pulse rate of healthy females has a standard deviation less than 13. So the pulse rate of healthy females has a standard deviation less than 13. First things first, what parameter am I testing here? Sigma, good. So you're testing sigma. And so our original claim is going to be what? Sigma is less than 13. So let's see if we can't fit that into a null and alternative hypothesis kind of setup. I'll give you a second to think on that. All right, so Abby, where should this go? Is this part of the null or alternative hypothesis? Chloe, is she right? That's a good question. I'm asking. Let me ask Grace
I
then.
think so.
Think so?
Yeah, I'm getting confused on when to know it's an HO or HA.
All right, so good. Good question then. How do I know where this goes? What am I going to look for that tells me where it goes?
Possibility, oh, sorry.
If it matches the original claim. Cause
Okay.
it's like HO is for like what it is like in words, and then HA is what it is like the opposite of what the.
All right, with it, you are going to have a heads and tails kind of opposite nature there. Ethan?
It's the possibility of equality.
Yeah, it's possibility of equality is really what tells you if it's going to be in the null hypothesis or the alternative hypothesis. So Cameron, which one is this going to land in, the null or alternative hypothesis?
Let's go the null.
Let's go with the null. That sounded like a mental coin toss. Not to pick on you. Is he right? Is it the null hypothesis?
The alternative hypothesis.
All right. The alternative hypothesis, because what is it missing? It doesn't have the possibility of equality, right? So in order to be part of the null hypothesis, it has to have one of these three. Equal to, less than or equal to, or greater than or equal to. So because it doesn't have the possibility of equality, it goes in alternative hypothesis. Creed, what has to be the, what's the flip side of this? Good, sigma is greater than or equal to 13. keep in mind that on my stat lab, they're gonna put sigma equals 13 here. I don't know, I like this better. On the test, if you wanna write this or this, that's fine with me. So, okay. Comments on that one?
Yeah, I got a question.
Yeah, please.
Did you just give us 13 or was it?
No, I just, this is a problem I just made up on the spot. The reason I did that is because I wanted to give you an example with a population proportion, population mean, and population standard deviation. So basically, you've got examples of all three of these. And in chapter 8, we're gonna do hypothesis tests for all three of these. So the work that you have to do to get those hypothesis tests is gonna be different than, you know, from one to the next, but, you know, you still can do it. So, anything else on these? Let's see. All right, so there's a link on D2L. If you'd open up D2L and find that link, that'd be great. It's gonna open up a little simulation that I'd like us to do. And to try and help you understand that simulation or the point of the simulation, I'm gonna do my own simulation here for us, but let me see if I got that link. Yeah, you should be able to open up a link that looks like this. And I think yours, when you open it up, will look pretty much like this. And let me kind of help you understand the point of this simulation with a simulation of my own. So, give you a chance to open that up. I'm going to pick this simulation. I'm going to toss a coin. We're going to simulate tossing a coin. And let's see, press OK. So let's toss a coin and see what I get. So let's press this one, and I got a head. And I got another head. Okay, so I got two heads in a row. Let me toss again. Oh, I got a tail, and then a head. You know what? Let me check the settings on mine, because this isn't quite doing what I want it to. Clear, yes. Escape, set. There. Change the weight. All right, let me try that again. So I want to toss a coin and just see what the results are. So let's see, toss, got tails, another tails, there's a head, tails, tails, tails. And this is getting kind of, you know, long in the tooth. So let me just toss it 10 times. And I've got 17 heads, or 17 tails and 3 heads. Let's toss it 50 times. Now I've got 70 tails and 13 heads. Toss it 50 more times. What do you think? Is this a fair coin? Do you think that I've got a 50-50 chance of getting this from a fair coin? I mean, maybe after the first couple tries, maybe you're like, okay, you know, you get 2 heads in a row or 2 tails in a row, that's fine. But after a while, you start getting a little suspicious. Like, well, wait a minute. That looks a little bit unusual to get that many tails with so few heads. And so we're going to do the same kind of thing here. Actually, this is more of an experiment about you than it is about probabilities so much. Well, I guess it's a little bit of both. So we're going to look at this distribution. Now the mean of this distribution is 100. But if you're sampling from a population, typically you don't know what that mean is. Maybe somebody claims that's 100, but you don't know. So you sample, and if the claim is that the sample, or the claim is that the population mean is 100, so H naught mu is 100. If you got a sample mean of 101, is that going to cast a lot of doubt that it came from this population? Not really. I mean, there's a lot of variability in these populations, so that you could easily get a sample mean of 101 from a population like this. So let's bump this up a little bit. In fact, I've got these probabilities kind of worked out for you on a slider. If your sample had a mean of 101, so let's just bump that up to 101, the chances of that happening correspond to this blue area underneath the curve right here, or purple area, I guess. And there's a 47.3% chance that that could happen. Well, let's go a little higher. Suppose, and you can drag this along as well, suppose that you took a sample from this population and your sample mean was 109. Now looking back at this, are you really doubtful? It's like, well, this could never happen, that couldn't be true. Or it's like, well, yeah, that could happen. The chances of this happening under these circumstances is about 27.4%. So let me write that down, 0.274. And I'll do one last one. Let's go up to maybe 114. So now that this area is getting smaller and smaller, that probability is getting smaller. The chance of getting such a value out of this distribution is 17.53%. Is that small enough to just say, you know what, I don't really think that the true population mean could be 100 because this is such a rare result? At what point are you going to get really skeptical? At what point are you going to say, nah, that can't happen? Now you can zoom this all the way up to 140, and you can see what happens to these probabilities as they go, as you get closer and closer to 140. And what you're doing is kind of the same thing we were doing with our coin toss, is we're flipping that coin and we're sampling, and the more data you collect, at some point you're going to get suspicious about this actually being true. That you're going to look at that and say, you know what, I just don't think that's true. Otherwise, I couldn't have gotten a mean X bar of this value. I want you to find for yourself what that value is. How high do you have to drag that slider bar? How small does this probability have to be before you really start to doubt that this could be true? We just did the same thing with flipping coins. After a while, when you get so many heads, you start to doubt that it's really a true 50-50 chance of getting a heads and tails. At some point, your mean, your sample mean, is going to be far enough away from this that you're going to start really doubting that that could be true. So adjust that slider bar. Find out where that point is for you. Now for my morning class, there's a good deal of variety in terms of where people wanted to put that mark. And we'll see what it is for us. But slide things around for yourself and see what you think. How high does this have to be before you start getting really skeptical that this the sample mean is coming from a distribution, a population with a population mean of 100? All right, so move that around for a bit and see what you think. So the parameter that's adjusting your sample mean is the B. So you can use that slider bar to adjust B. And at some point, you're gonna get to a place where the probability is so small that you say, you know, I just don't think this could happen. And I wanna know what that point is. If you notice, they have so red is here to the left,
I don't know.
here to the right. We're just looking at the tail. Yeah.
It's not even like this. In the blue number, this is corresponding.
Yeah, so that's gonna be your tail. So as you move the slider, you'll see that area's gonna decrease, probability's gonna increase. So at what point you're like, you know, I don't think that could really happen very easily. I don't think that the mean is actually 100, because our sample mean contradicts it so much. In fact, it was funny, like there was like 4 people that had 125 all inside of the room. So they're staying consistent with that. Probably want to slide it more, because that's, chance of that.
Chance difference.
Notice that this is one.
Some people might have heard that change.
It's like going. I don't know. It's about music.
We'll see. Okay, so let's take a look here. You know, the question is, you're drawing from this, your null hypothesis is that the population mean is 100, but your sample means seem to contradict this. Sample mean of 109, sample mean of 114. At what point does your sample mean contradict this so much that you really say, you know what, I don't believe this is true? Now that's a question that you can answer, and I asked you to answer. So what values did you get that you finally said, all right, that's it, that's high enough? What kind of numbers did you get? I know a few people got 125. Cameron, what'd you get?
24.7.
124.7. There was a few 125s over there. But there were some higher numbers too. Jacqueline, what'd you get? Jaslyn, what'd you get? 130? Okay, 130.
I got 124.
124, okay.
121.
121?
I got 135.
135, all right, good, good. Jaren,
125.
125? Something else for variety.
I said
I had 134.
134, and what else?
130.
130? All right. So there's a lot of variety here, right? I mean, it's kind of a little bit of a subjective thing. But as far as it goes for this class, our kind of line in the sand is the same thing we used earlier. Our rare event rule was less than 5%. And let's see when that happens for this distribution. So let's see. So the number we should be paying attention to is the one down here. So yeah, somewhere around here, about 125. It's starting to get kind of small, all right? So if there's a 1 in 20 chance that this could happen, that means 95% of the time it shouldn't be happening. So, you know, somewhere in there you can be skeptical. But what you're getting at, what we just calculated, is something called a p-value. So, p-value. And let's talk about what a p-value is. And Let me do that on this next sheet here. The p-value is the probability that H naught is true given your data set, or for a given data set. Probability that H naught is true for a given data set. Okay. Now the form of the calculation, how you're going to get the p-value is going to depend on the form of your alternative hypothesis. And I gotta apologize, I made a mess of this down here because I put HO. P-values are going to be based on the alternative hypothesis. So if the alternative hypothesis looks like this, and these are just my own made-up examples, if your alternative hypothesis is HA such that P is greater than, say, 0.25, that's going to be a right, I need to do a left tail test here. My bad. Let's just change that up for this one, just to be consistent. This is going to be a left-tailed test. If you had HA such that P was greater than 0.73, and again, I'm making up this number here, that's going to be a right-tailed test. And what you should notice about the tail of the test is kind of a helpful little mnemonic of sorts. And that is, the inequality points in the direction of the tail. So for a left-tail test, the p-value is just going to be the area in the left tail. For a right-tailed test, I screwed this up again, didn't I?
Yeah.
Yeah, for a right-tailed test, I should have put this up here. I'm sorry. Right-tail test would be 0.73, and then a two-tail test is when you have a not equal to in the alternative. So a right-tail test is what we just had, is when you're trying to find the area in the right tail of a certain distribution. In this case, there is the normal distribution. And finally, a two-tailed test, that area is going to be in both tails. So the area for a two-tailed test is a not equal to. Right-tailed test, P is going to be greater than some number. Left-tailed test, P is going to be less than some number. So the form of the alternative tells you what tail you're looking for. Now, a couple things. I mean, if you were to take this and you wanted to fix it, first of all, you'd have to correct all these H sub zeros should be H sub A's. I'm not going to go through and correct all that stuff. I want to spend a little time talking about this one, which is a homework problem. Which of the following is not true about your p-values in hypothesis testing? Well, the first one is true. The p-value is an area. It also corresponds to a probability. It has both interpretations, so we're okay with that one. Another thing that they say about the p-value, or what we're going to do with the p-value, is it's going to help us decide when we're going to reject the null hypothesis and when we're going to accept it. And so let me write this in big bold letters for us. Reject H naught if the p-value is less than alpha. Now that's the same alpha that we've used before. It was the alpha that we used to find z sub alpha over 2. It's the alpha that we get when we're talking about a confidence interval. Our confidence intervals, we had like a 95% confidence interval. Our significance level is 1 minus our confidence level of confidence. So that's that same alpha. The author has a little mnemonic device. If P is low, H naught must go. Meaning reject H naught if the P value is less than your alpha. So reject H naught if P is less than alpha. That's what this is supposed to help you remember. And that's what we have down here. If, actually, the bottom one, if the p-value is low, H naught must go. He's got another one. I don't find it as helpful. If the p-value is high, the null will fly, meaning, all right, you're just going to fail to reject H naught. So the one that doesn't work is this second one, B. P-value separates the critical region from the values that do not lead to rejection of the null hypothesis. That's not true. That'd be something called the critical value. All right, so let's practice this a little bit. And we're going to do it with some of the problems in example B. Anyone need me to move around? You got all the information we need from up here? Example B looks like this. We've got z equals 1.18 as a test statistic that's obtained when testing the claim that P is not equal to 0.282. Well, that gives us a chance to practice our null and alternative hypothesis stuff again. HO and HA. Our original claim is this. P is not equal to 0.282. Is that going to be part of the null or alternative hypothesis? Gabby, did you?
The alternative.
Victoria, is she right? Yes, thanks ladies. It's part of the alternative hypothesis, 0.282. Now how about the null hypothesis? If that's part of the null hypothesis, great. What has to be part of the, or if this is part of the alternative, what has to be in the null?
P is equal to 0.282.
Yeah, P is equal to 0.282. Nice. All right, so, what tail test is this going to be? It's going to be a right tail, a left tail, or a two tail. What tail test is this going to be? Two tail test. So really what we need to do to figure out the p-value is this. Let me draw our distribution. Here and here. So we need to figure out how much area is in the tail to the right of 1.18 and to the left of negative 1.18. So kind of the mirror images. I need the area here plus the area here. That total is going to be our p-value. All right. Now for this, you're probably going to want to take out StatDisk. You could use Google Sheets, but StatDisk in this case is going to work out much easier. So let's open up StatDisk. Probability distributions. What distribution am I working with? A Z is what distribution?
Normal.
Normal. Something I hope you remember is that Z is the standard normal distribution. So I would write Z is distributed normally with a mean of 0 and a standard deviation of 1. There's an infinite number of normal distributions, but there's only one standard normal distribution. We use Z to denote that distribution. You can find probabilities and areas underneath the Z-curve with Google Sheets, but there's something here in StatDist that makes it really easy. So cumulative area to the left, no, we don't want that. We've got the Z value, it's 1.18. It's given us a lot of different areas and probabilities. Which one's the one I want here?
Two-tailed.
There's 5 cumulative probabilities. Which one?
Two tails, right?
Ah, two-tail. Good on you. It's exactly the one we want. So what it's doing is it's taking the area in both tails and adding it up. Now, if you take a look here, there's the area in the right tail. The area in the right tail is 0.1190. By symmetry, that area also has to be the same in the left tail, 0.1190. So you could take your calculator and add those up, but if you did, you would get the exact same thing as that I'm going to get over here, which is 0.2380, which is your p-value. It's the area in both tails. And that, and who was it that gave it to me? Is this area right here, the two-tailed area, 0.2380. Who got that first? Well done, Imran. All right, so that's your p-value. Let's put the p-value together with something else to do part C. Before I move on to part C, are we okay with part B, how we found the p-value? All right, it's based on the form of the alternative hypothesis. It was a two-tailed test, so we found the area of both tails, and it's 0.230. So part C says, okay, let's assume we have a level of significance of alpha of 0.05. If that's true, should we reject H naught or fail to reject H naught? So we've got two choices, here or here. And I like this, they say reject H naught or fail to reject H naught. One thing you want to keep in mind about your hypothesis test is that we're never proving H naught is true. You don't prove something true if you're assuming that it's true. And our hypothesis tests always work by assuming that H naught is true. Well, what do you think? Should we reject or fail to reject? Go back up to here. Is your p-value less than alpha? Is 0.2380, is that less than 0.05? That's false. So does that mean reject or fail to reject?
Reject.
Fail to reject. Good, fail to reject. It's not less than 0.05. If it was less than 0.05, then you'd be rejecting. No questions asked. But it's not. So basically what's happening is you didn't find enough evidence to convict. You didn't find enough evidence to get rid of H naught. And that's it. Okay. Let's keep going. Test statistic is Z equals 1.79. Let's highlight that. Obtain when testing the claim that P is greater than 0.2. So that's your original claim. Let's see. So our original claim is that P is greater than 0.2. Let's use that to set up the null and alternative hypothesis. H sub O, H sub A. Justin, is this going to be part of the null or alternative hypothesis? Null? Is she right?
Alternative.
Does this contain the possibility of equality?
No,
So where does it have to go?
Bernadette.
Has to go in the alternative, so it's gonna be P is greater than 0.2. Thank you. Johnny, what should the null hypothesis be?
Less than or equal to 0.02,
Perfect.
or 0.2, sorry.
Yeah, no worries. P is less than or equal to 0.2. Notice you've got that possibility of equality. What's my stat disk gonna write it like, or my stat lab, I should say? They're not gonna put the less than or equal to, what are they gonna put?
P equals 0.2.
P equals 0.2, yeah, just something to be aware of. I think it's a little friendlier doing it this way. We'll continue to do it that way.
That would only do for the HO, right?
Yeah, that's only for the HO.
Okay.
Is that they're not gonna do the less than or equal to or greater than or equal to. It's just all, for them, it's just gonna all be equal to.
Right, but for the HA, it would be greater than, right?
Yeah, HA is gonna have to have greater than, less than, or not equal to. Let's see. Ben. This is gonna be a left tail, right tail, or two tail? Right tail, excellent. So let's draw ourselves a little right tail distribution. And let's see. So we want to find the area in the right tail corresponding to a z-value of 1.79. Again, you could do this on Google Sheets, but when you're talking about z-values, it's just easier to work with StatDisk. Now, why didn't we use StatDisk all along? Well, because StatDisk only works with z-values. If you have a value that's from a distribution other than the standard normal, like a mean of 100, a standard deviation of 10 or 15, like intelligence, you'd have to do a transformation or use Google Sheets. So there we go. Which area do I want this time?
Right.
The right tail. So that right tail is 0.3673. 0.03673. And bam. So the question is 0.03673, is that less than my alpha, which was 0.05?
Yes.
And the answer is yes. So do we reject H naught or do we fail to reject H naught?
Reject.
Reject. Good. If this is low, meaning lower than alpha, H naught must go. You're going to reject it. So the answer is reject. So let's just circle that and put it in with our conclusion there. Nice. Reject H naught. Cool. Comments or thoughts on that one? The tail of your test, like I said, is going to be determined by the direction of that inequality. Now, the first couple that we did here were with, hypothesis for a population proportion. But it's going to be the same is going to be true if we were doing with a population mean or a standard deviation. That is, the direction inequality in the alternative tells you if it's a left tail, right tail, or two tail. And it's the same for all of these. Now, a lot of times, instead of an actual number here, like I wrote you in this example, what you'll see is a mu naught or sigma naught, meaning, all right, it is an actual number, it's not the parameter. All right. Let's see how we're doing here. 8.1. I do not like example C. we are gonna skip example C. It's just not very well written. But the conclusion I would get is that if you had a mean IQ of students, if your claim was that the mean IQ was greater than 110, and your simple random sample revealed a mean IQ score of 125, yeah, that's evidence that the mean IQ is greater than 110 is true. So I would get rid of the middle two options here. But boy, looking at these other two, I really don't like either one. I promise to be more careful than this in writing a conclusion for you. In fact, you're going to be writing your own conclusions, and we'll practice that more and more, especially as we get into section 8.2. But 8.2 is not going to be on the exam. As far as the correct answer for this one, let's see. Sample is not unusual if the claim is true. Sample is not unusual. I'm not really happy with this second part of this. Although I think if I had to choose between these two, I'd go with this one, D. But like I said, I just don't really like D at all. So, anyways, you will run into some of this kind of thing at home, homework. But for now, I think I'm going to divide this video up into two parts. So